Good afternoon. Colleagues, students, and guests, welcome. I am Inga Musselman, Vice President for Academic Affairs and Provost for the University of Texas at Dallas, and today it is my pleasure to welcome you to the 2023 edition of the Polycarp Kusch Lecture Series, Concerns of the Lively Mind. In a few minutes, Dr. Stephanie Adams, Dean of the Johnson School of Engineering and Computer Science, will introduce today's lecturer, Dr. Mark Spong, Professor of Systems Engineering and Professor of Electrical and Computer Engineering. But first, I would like to share a little background about Dr. Polycarp Kusch and the lecture series. You may know that Dr. Kusch was a member of our physics faculty for 10 years, from 1972 until his retirement in 1982. First as Eugene McDermott Chair, and then as Regental Professor. Dr. Kusch came to the University of Texas at Dallas to help build a new university in a cotton field near Dallas. A university that from the outset was destined to be, in his words, not quite like the ones that were in existence at the time. This was immensely appealing to Dr. Kusch. Dr. Kusch was born in Blankenburg, Germany in 1911. He was educated at Case Western Reserve University and the University of Illinois. He spent much of his career at Columbia University in New York City, where he was professor of physics. At Columbia, he also took on administrative roles as physics department chair, vice president and dean of the faculty, and then Vice President for Academic Affairs and Provost. In 1955, while at Columbia, Dr. Kusch was awarded the Nobel Prize in Physics with colleague Dr. William Lamb for their contributions to the knowledge of the atom. In collaboration with another Columbia physicist, Dr. Henry Foley, Dr. Kusch conducted experiments to precisely determine one of the electron's most important physical properties, the magnetic moment. This work has been instrumental in the development of new technology, including magnetic resonance imaging, or MRI. In addition to the Nobel Prize, Kusch was awarded 8 honorary degrees, and he was elected to membership in the National Academy of Sciences, among other honors. A longtime educator, Dr. Kusch was not only an eminent physicist, but also an award-winning teacher. It was reported that Kusch dearly loved his work, especially the teaching. As he once said, "I describe myself as an adequate scientist, but I am a superb teacher." At Columbia, Dr. Kusch was chosen to teach an introductory physics course for non-science majors, informally known as Physics for Poets. Columbia awarded him its Great Teacher Award. At UT Dallas, Dr. Kusch was known for his lecture demonstration course called The Phenomena of Nature, for which he assembled a first-rate collection of equipment to show physicists and non-physicists alike just how nature works. Following Dr. Kusch's retirement in 1982, and to honor him, the University of Texas at Dallas established the Polycarp Kusch Lecture Series. And each spring since 1985, with the exception of 2020 because of COVID, one of our esteemed faculty colleagues has delivered a lecture with a theme related to concerns of the lively mind. At this time, I would like to recognize any former Kusch lecturers who are here today. If you're a former Kusch lecturer, please stand to be recognized. Through the annual Kusch event, the University of Texas at Dallas simultaneously honors a former colleague, Dr. Polycarp Kusch, and a current distinguished colleague. And today, that colleague is Dr. Mark Spong. Dean Adams, please come forward to introduce Dr. Spong.
Thank you, Provost Musselman. Good afternoon, and thank you for joining us today to celebrate Dr. Mark W. Spong and the legacy of Dr. Polycarp Kusch. No introduction could fully capture Mark's contribution to education globally or here at UT Dallas, but I will try to highlight a few aspects of his legacy. As an educator, Mark co-authored one of the most popular textbooks on robotic dynamics and control, which is still in use after more than 30 years. As an innovator, Mark created solutions to control problems, then built machines to test and prove theories. His solutions stand the test of time and became the new foundation and standard in the field. In true educator fashion, he does so in very interesting ways, such as developing the first robot that could play air hockey as a vehicle to investigate research issues in real-time control, machine learning, and computer vision. What you will experience today is Mark's brilliance in the closely related fields of robotics and control. As a businessman, Mark founded Mechatronics Systems Incorporated, which markets both hardware and software he developed, and that is being used by more than 200 universities around the world. As a leader, Mark served as the 4th dean of the Eric Johnson School of Engineering and Computer Science. Mark modeled excellence in research and brought transformative growth, overseeing an enrollment increase from a little more than 2,700 students to over 7,000, and the expansion of faculty, endowments, departments, and buildings. He also created the corporate-sponsored, team-oriented, award-winning capstone experience known as UT Design. Mark is respected by his peers, as evidenced by the numerous accolades from the most prestigious organizations in engineering, including being a fellow of the International Federation of Automatic Control. He's also a fellow of the Institute of Electrical and Electronics Engineers, a recipient of the IEEE Third Millennium Medal. He also earned the Nyquist Lecturer Prize awarded by the American Society of Mechanical Engineers and the John R. Ragazzini Award and the O. Hugh Shuck Award from the American Automatic Control Council. Lastly, Mark has made it very hard to follow in his footsteps as the 5th dean. For some, having their predecessor on the faculty, it could have been awkward or uncomfortable as they bring forth a new or enhanced vision. But Mark's character and respect for me and the office has allowed us to both coexist with no fanfare. He continues to make himself available as a sounding board to me whenever I call, and for that I'm especially grateful. I personally am excited to hear Mark speak today, so without further ado, I present to you Dr. Mark W. Spong, Professor of Systems Engineering and Professor of Electrical and Computer Engineering, on the lively mind topic of robotics, past, present, and future.
Well, thank you, Dean Adams, for that very kind introduction, and thank you, Provost Musselman, for choosing me for this award. Maybe I can increase the volume a little bit. Don't know what I'm doing here, but if that gets too loud. Well, thank you all for coming. Having been on the other end of this decision, I know I know how important it is for the deans and how seriously the deans take this, their choice and recommendation for the Kusch Lecture. So I thank you for choosing me and all my current and former colleagues. After I was asked to give this lecture, 2 interesting things happened. The first was the tremendous publicity that has come about surrounding ChatGPT, the artificial intelligence program, and artificial intelligence in general. The second was 3 weeks ago, I myself underwent a robotic surgery procedure. So as I was going under, couldn't help but thinking, I hope the engineers that designed this robot graduated from a good school. But everything turned out okay. So my work, as Dean Adams mentioned, my work has been at the intersection of control theory and robotics. So control theory is somewhat unique in that it's both a branch of mathematics and a branch of engineering. And of course, robotics itself is very interdisciplinary. You find robotics in computer science, electrical engineering, mechanical engineering, bioengineering. systems engineering. Okay, so most of my presentations, of course, are technical, involving a lot of mathematical underpinnings of robots and control. So I'm going to spare you all the mathematics, which I'm sure you'll be grateful for, and kind of give you a higher level presentation. As you see, talk about past, present, and future, and I hope we'll have a little bit of fun at this. So each of these topics, of course, is very large, could fill a whole more than the time I have allotted. So I'm going to talk a little bit about the past, and if we're going to talk about robots, we should be able to define what is a robot. If we ask you, what do you think a robot is, how would you define a robot? So we'll talk a little bit about that. And then I want to talk about something that's called Moravec's paradox. And if there's one takeaway from this talk, it should be that whenever you hear about artificial intelligence and robotics, robots doing our day-to-day tasks, think in terms of what Moravec's paradox has to say about that, and we'll get to that. And then I'll talk about autonomy. Autonomy being the holy grail of robotics. What does it mean for a robot to be autonomous? And give you a few examples. And in the future, I'm going to talk about a couple of specific areas that I think are important for the future. I'll mention humanoid robots, networked robots, human-robot interaction, which is extremely important these days, and telepresence. So that's kind of where we're headed. Now, the history of robotics, of course, goes back even pre-classical, okay, before even the Egyptians, the Greeks. People were interested in building artificial humans, animals, and so on. We don't have time to talk about any of that, but there is a long history of mechanical animals, dolls, and what were called at that time automata. Prior to the 20th century, things like a mechanical horse, steam-powered mechanical man, lots of dolls, and so on. I'm not going to go farther back than that, but there's an interesting example of the golem, which in Jewish folklore is an animated humanoid. So certain rabbis had the power to create golems out of clay and bring them to life. And actually, the golem is mentioned in the book of Psalms in the Bible. The most famous golem legend is probably that of Rabbi Loew of Prague, who created a golem in the 16th century to protect the Jews of Prague. And in some accounts, the golem eventually went on a murderous rampage and killing the Jews. So it seems that golems, once created, are difficult to control. Well, that influence of the golem is actually seen in many stories, like The Sorcerer's Apprentice, Frankenstein, and a number of others. So it goes to the somewhat distrust in Western culture of science in general, and the idea that you create something like The Sorcerer's Apprentice and something goes wrong, right? Many people know that the word robot itself was introduced in the English language by Karl Čapek, a Czech playwright, in his play called Rossum's Universal Robots. And the word robota in the Czech language actually means laborer and has a connotation of a forced laborer. It was actually his brother, who was an artist, that suggested the name. He didn't know what he was going to call these creatures, and his brother said, why don't you call them robots? And so the name has stuck. The play begins in a factory that makes artificial people, called roboti, and they're happy to work for humans at first, but eventually they rebel and the human race is extinguished. Two of the robots, Primus and Helena, develop human feelings, fall in love, and become the new Adam and Eve to populate the world. So if you're interested in robotics, you should read the play. I think it's probably not a coincidence or not unusual that this came out of Prague, that Karl Čapek had this idea of this story because of the influence of the golem going back to the 16th century in Prague. So the modern industrial robot actually dates from 1954, patent by George D. Vall, and he didn't call it a robot, he called it a programmed article transfer device. Joseph Engelberger bought the rights to his patent and founded Unimation Corporation. So the first Unimate robot was installed in a General Motors plant in New Jersey in 1961 to tend a die casting machine. Basically, it was the robot arms that you see in factories, took a part out of the die cast, stacked it, took another part, stacked it, and so on. The first robotic welding line of 28 robots was at the General Motors Lordstown, Ohio plant in 1970. And this I find interesting because in 1970 I was a high school junior about 10 miles from the Lordstown plant. I grew up in this area. So I remember well when they built that factory. Okay, that's all the time we have for history, but we now have many things besides manipulator arms that we call robots. So if I would ask you to define a robot, how would you define it? We have many things that we call robots: humanoids, robot surgery systems, drones, vacuum cleaners, Mars rovers, and so on, okay? So in fact, the term robot has become quite overused, right? How many of you go to a website and you have to check a box, I am not a robot, before you can go to the website, right? So we have robots crawling the internet, robot toasters, robot lawnmowers. You can go to Amazon and find a robot cat litter box. You can find a robot holster, which is something you clip to your belt and you can clip your iPhone to. So the term has become somewhat meaningless. The companies figured out that instead of selling a crock pot, if they have a robot crock pot, they can increase their market share. So, but if you go to the robotics community, the research community, there's a popular definition that people will tell you that a robot is a machine that transforms sensing into action. So here we have the environment. The robot has some sensors to collect data, sense the environment, has some computation to analyze the data, compute commands to give to the actuators to act back on the environment to do some work. Well, in the field of control, of course, if you say, what is a control system? This idea of sensing into action is actually the central concept in feedback control. So it's hard to distinguish these two definitions of a robot, a machine transforming sensing into action, and a feedback control system, which also transforms sensing into action. So for me, without feedback control, there's no robot, okay? And action essentially means manipulation or locomotion. Manipulating objects, moving around from place to place, and so on. So my definition, I modified a little bit. My definition of a robot is a machine that transforms sensing into action through feedback control capable of manipulation or locomotion. And in fact, in these two, we'll see some examples. Manipulation is really the harder of the two tasks. Because of locomotion, we have wheeled vehicles. There have been great strides made in, no pun intended, great strides made in walking robots with bipeds, quadrupeds, and so on. We still have a long way to go to build robots that are capable of really good manipulation. Well, that leads into what's called Moravec's paradox. And Moravec's paradox, the way it's stated, is that low-level sensory motor control tasks require enormously more computational resources than high-level reasoning. Well, what does that mean? Well, since we're at UTD, the best example I can give you of that is robot chess. So we have chess programs, of course, algorithms that can play at the grandmaster level, but a small child can manipulate the pieces on the board better than the best robot. So why is that? Well, one explanation is that sensory motor control has had millions of years of evolution to develop. High-level cognitive skills are much more recent from an evolutionary standpoint, right? If you encounter a lion on the savannah, you'd rather be a good runner than a good chess player, right? So this has a lot of implications in terms of capability of robots. The oldest human skills are largely unconscious, and so they appear to us to be effortless. Skills that appear effortless to us are actually among the most difficult to reverse engineer. Things like walking, running, grasping, catching, and throwing are actually quite difficult to build a robot to do these. So the easy answer, or the easy way to state this, is things that appear easy for us are actually hard for robots. And conversely, things that we think are difficult, like figuring out chess strategy, are actually easier for artificial intelligence programs to accomplish. Well, another implication of that is if you think of jobs that are going to be automated, jobs that are easy to automate, well, things like bank tellers, paralegals, customer service representatives, editors, and proofreaders, these are jobs that do not involve significant manipulation or locomotion. Jobs that are difficult to automate, landscapers, chefs, housekeepers, auto mechanics, and so on, these are jobs that involve significant manipulation or locomotion, and they're actually very difficult to automate the job of a landscaper or a housekeeper. Here's a project that is out of Berkeley. Let's start this. This is a towel folding robot, and this is a big deal when they did it. So here you have a robot with 2 arms, camera to sense to try to identify the towel, sense the shape, and so on. Now I have to tell you, this video is sped up 50 times, normal speed. So would you rather, if you're a hotel, do you want a minimum wage housekeeper or do you want a $200,000 robot that takes 20 minutes to fold a towel? So this is the Moravec's paradox. It's very difficult to get robots to do these sort of manipulation tasks. Okay, so we hear a lot about robot autonomy. Okay, we have autonomous vehicles, we have autonomous drones. Okay, what do we mean by robot autonomy? Well, autonomy refers to action without human control or intervention. And we think of autonomous robots as somehow being intelligent, but are they really intelligent? Okay, what does it really mean? What is the current state of the art in autonomy compared to something we might classify as real intelligence? Well, David Mindell, if you read his work, he says autonomy connotes a broader sense of self-determination than simple feedback loops and incorporates ideas from artificial intelligence and other disciplines. And the point of that is what we call autonomous robots today are not really autonomous in the sense of being artificially intelligent. The current level of autonomy in robotics does not represent an ability to reason or make decisions beyond what the control system designers intended. So let me give you an example of that. This is from our lab here at UTD, some things my students did. Here we have a network we have 4 ground robots, and we have a drone. And the basic idea here is the robots are commanded to follow a certain path, avoid collision with each other, and they have sensing capability. They know if they're getting close to another robot not to collide. The drone basically is given a task, just follow the configuration of robots. Follow that team of robots around. Now this is completely autonomous in the sense that once it starts, there's no human interaction. The robots are doing what they're programmed to do, following trajectories, avoiding collisions. The drone is following the tack, keeping the formation in view. And this is essentially, although this is old, and we have a lot more work going on here at UTD that has extended this quite a lot. People in our engineering school, Tyler Summers, Justin Roos, Justin Kuhl, and others have extended these ideas. But this is essentially the state of the art in autonomous robots, including autonomous driving. Okay? But it does not represent true intelligence. They're doing what the programmer tells them to do, and they're doing it without human intervention. So the best implementations of autonomous robots are really the result of superior modeling and feedback control in artificial intelligence. So my claim is that artificial intelligence is really not going to produce intelligent robots. What artificial intelligence is going to do is improve the performance of our autonomous systems. And you see this little food delivery robot on campus all the time, right? I've been doing this for 45 years, and I still stop and watch these. These guys still make me smile, right? You can't help it. So they stop at the corner. If they see you get close to a pedestrian, they stop and wait, and it's a lot of fun just to watch them. But are they intelligent? Well, this is a particular application that is well suited for this type of robot because there's a well-structured task, right? They move from point A to point B. They have a well-structured environment. They have a map of the campus. They know where all the sidewalks are, the roads are. There's no uncertainty there, okay? And they can sense people, obstacles, cars, and so on. And there's a simple control. The task does not involve manipulation. Locomotion is simple because the wheels are easier to control than legs. So artificial intelligence will make this better, better able to recognize people. For example, maybe there's a bicycle, the censoring, the algorithm in the perception system might say, well, that bicycle doesn't have a rider on it, so I don't have to worry about that. I can just keep going. But if the other bike has a rider, I better stop and wait for that. So there are a lot of ways that AI can improve the performance, but the basic structure is the basic application, which translates to autonomous vehicles, autonomous drones, and so on, is kind of a well-structured task that's good for robots to do. All right, so in terms of the future, the humanoid robot is kind of seen as the ultimate goal, right? We want to build machines that are like us, okay? So the question, though, is, should this be the ultimate goal? Okay, well, if you think back in terms of more of its paradox, the development of a general purpose humanoid is actually called general intelligence, okay? And the task of building a general purpose, general intelligent or artificial intelligent humanoid is quite a challenge, right? And we're not close to having a robot that can really serve as a general purpose robot. And the question we ask is should this really be our goal? In other words, is the future going to be rosy or Roomba? Okay? Well, my money's on the Roomba, okay? And one of the reasons to tell you is that there's something that you can look it up. It's called the uncanny valley. And the concept suggests that humanoids that look too much like us give us a kind of an uncanny feeling of uneasiness or even revulsion, okay? So the valley denotes a dip in the human observer's affinity. We have these cute little robots on the right here. We like them, right? If it gets too much to looking like humans, they become from cute to creepy, right? So, and that's been well recognized as what's called the uncanny valley. So, there's an interesting story about the Roomba that I heard secondhand, but I believe it's true. Is that another reason we like robots is that we anthropomorphize them. So you don't need to be rosy for people to have an affinity for their robot. There was a family that had a Roomba vacuum cleaning robot, and it broke, so they sent it to the company for repair. And the company said, well, we cannot repair this, we're going to send you a new one. And they said, we don't want a new one, we want Alice back. So the idea of a $1 million humanoid robot with limited capability is perhaps not the ultimate goal, okay? So a humanoid robot would say, go to Subway, make your sandwich for you, put it in a bag and deliver it to you. Well, we're a long ways from doing that, right? We have the food delivery robots that are in a well-structured environment, and they can do that, but somebody else has to actually manipulate the meat and cheese and mayo to make the sandwich, right? Okay, so I would argue that humanoids outside the entertainment industry, right? Humanoids right now are primarily in the entertainment industry, and they do a great job. You know, you have a robot that can speak to you. You could actually interface ChatGPT to the humanoid robot and ask it a question. It can formulate an answer, okay? But it's going to interact with you verbally, maybe some facial expressions, but it's not going to cut your grass or make your bed, okay? It's not going to do useful work. So the humanoids, I think, have their place in things like entertainment, but I'm going to argue that the future of robotics really lies in the confluence of three areas. And these are what are networked robots, human-robot interaction, which is extremely important, and telepresence. And I'll discuss each of these in turn, maybe give you a couple examples. So why are humans successful? Well, we're successful because we work together. No one is an island. We work together, we form teams, we collaborate. Well, by networked robots, we mean a group of independent robots that can function as a single coordinated entity by communication and cooperation. So rather than one expensive monolithic robot, you have multiple inexpensive robots that get their functionality by collaboration, working together. Applications include things like surveillance, environmental modeling, health monitoring, cooperative manipulation, vehicle formations. Agricultural robots is a big application because, again, it's in a well-structured environment. Here's a little example, again, very simple experiment that we did with Tokyo Institute of Technology. These are 4 robots that each robot can basically sense robots within some distance away from it. And the motivation is, think of a school of fish, right? Each fish can sense only maybe its nearest neighbors. How does the collective behavior of a school emerge from the local information when each fish can only have limited sensing? So each robot can sense any robot that comes within a certain radius of it. And the goal here is just, we told the robots, just point in the same direction. Find out what your neighbor's doing and point in that direction. And the emergent behavior is they should all eventually point in the same direction. We start this. And the student puts in what looks like a fake robot. They don't know it's a fake. They'll orient to that. It's like a leader. Okay, he can actually control the whole formation and get them to orient in any position they want. The little graph on the right shows their sensing radius. And when he moves it to the other side, you can actually see information flow through this network. First, one robot sees it, then the other robot sees it, then the third robot sees it, and they eventually orient themselves all in the same direction. Okay? And there's no central control here. They're just told to look at everybody around you and try to mimic what they're doing. He puts it in the middle, they all see it at the same time. Okay, so an example of networked robots. Second topic is human-robot interaction. Okay, when I was starting out, of course, robots were big, dumb, and dangerous. Humans had to be physically separated from robots. Now, robots are designed to work very closely in collaboration with humans, even inside the human body, right? And I think this has been the biggest change in robotics in the past 30 years. And I think one of the most important areas in the future is to pursue human-robot interaction. Applications are assistive robots, hospital robots, rehabilitation, exercise trainers, household robots, and so on. And this raises important issues of safety, psychology, socioeconomics. These are problems engineers can't solve alone. We need to get social scientists involved, psychologists involved, and so on. Because it's not the robots themselves or the humans themselves, it's the interaction that leads to kind of new problems, new areas of research that need to be pursued. Dean Adams actually mentioned the air hockey robot. I want to put this up because this was something that we did in the 1990s. Okay, human-robot interaction was not even I didn't even know that term. Okay, so I didn't realize that we were doing human-robot interaction at the time. But the National Science Foundation had a new program that they called Intelligent Control. Nobody knew what intelligent control meant, and I think we still don't know what intelligent control means. But we decided to put together a project to try to study the integration of control theory with real-time computer vision and machine learning. And that was, we call it intelligent control. Now you have to remember that everything I'm talking about, everything you see today, and all the advances in AI, robotics, and so on, it's really a consequence of Moore's law, that the power of computers has been increasing every 18 months to 2 years for several decades. So the power of computers have reached the point where we can analyze huge data. We can take 1 million training samples and analyze them very quickly. Okay, when we started this project in the 90s, computer vision was a very hard problem because it was very slow. And now you have a webcam on a drone, and it can do control in real time. We couldn't do that. So in order to try to test our theories, we came up with this idea, why don't we build an air hockey robot? Why? Well, because it's a very fast game. We built a robot shown here, put a camera in the ceiling, and to try to sense the location of the puck on the table. But the vision was so slow that maybe we only got 1 or 2 samples if the puck was moving quickly. So it was a real challenge to do real-time vision. And it was repetitive. So perhaps over time you can learn to do better, okay? So there were control challenges, vision challenges, and machine learning challenges, and this was the vehicle we chose, okay? So my student here in the purple is Brad Bishop. That was his PhD thesis. He's now the department chair of the Systems Engineering Department at the U.S. Naval Academy, teaching robotics to midshipmen, and he did a great job on this. So here's a very short, I have more video, but very short video showing that some performance.
He was inspired to a great extent by the work of Kusch and Kusch, who have developed a 3-degree of freedom weathering robot. While juggling can be likened to running over level ground, in the sense that both involve the establishment of stable periodic motion, air hockey can be likened to running over highly irregular and uncertain terrain where frequent gait changes are necessary and real-time vision must be used to generate suitable foot placement. Thus, robot locomotion forms an important long-term goal of our research.
So something that I didn't have time to talk about is kind of a duality between manipulation and locomotion. We kind of thought that when you're walking, you're kind of interacting, manipulating the ground. This air hockey controlling through impacts is kind of like running over irregular terrain where you have to use your vision for foot placement and so on. But what was interesting about that is we actually programmed in, again, there's nothing artificially intelligent, it's merely a control system that takes the sensory data and has some algorithm to figure out where to move the paddle, right? But we programmed in what we called a confidence measure. Because the puck vision was difficult and the puck may be moving fast, we devised a confidence measure that was based on the reliability of our sensory data to say, well, if the confidence is below a certain level, play defense. If your confidence is higher, play offense. And when you play with this robot, you couldn't tell what it was going to do, whether it was going to play defense or offense. So it was in that sense, it was the behavior that came out of this was hard to predict. And now, of course, you could build an air hockey robot with very fast multiprocessor, multi-core architectures, and so on, much easier than we could do. Okay. The last topic is telepresence. Telepresence, of course, means having a sense of presence. You're present at a distance. And this leads to what I call semi-autonomy. And again, semi-autonomy is, again, humans and robots working together. The story I like to tell, this is a kind of an old slide that I've had for years, but suppose you want to build a moon a base on the moon, you want to do some construction, or plan to go back there soon. Well, it's very expensive to send a construction crew. Okay, robots can't do fully autonomous robots can't build a house by themselves. So maybe you send a large number of robots and a very small number of humans. Now the human could be in lunar orbit, could be in Earth orbit, controlling the robots through some haptic interface, say. And you have problems like communication networks. There's things like delays, reliability of communication. Here the robot formation is shown here, say manipulating a common object. So here now they have their local intelligence. They know enough to maintain their formation, like we saw the formation of robots. And the human with one interface can control the entire formation. So humans can control one robot, say with a joystick, but how do you control an entire formation? They have their local intelligence, which is the autonomy part, and the semi-autonomy is the human says, move that table from here to here, and the robots as a group can do that. So this involves networking, human-robot interaction, and telepresence all in one. It's another application that I presented. If you look at a modern commercial aircraft, like an Airbus, okay, the pilot sits in the cockpit in the seat. Everything is basically computer controlled, right? He's got a heads-up display. He or she has a heads-up display. more or less controlling through a joystick. So a modern commercial aircraft is basically being teleoperated by the pilot through computer control. So the pilot really does not need to be in the aircraft at all. It could be in the control tower at DFW and still control the robot. Okay, so here you could have a platoon of vehicles that maintain their own formation. Maybe they're flying from DFW to Tokyo, taking cargo. And when they get there, the pilot can log in and land one, switch to the other, land the other, and so on. Same thing with a platoon of transport vehicles. Maybe they're in a war zone. You can make the driver in a safe location. We have, of course, now, we have pilots in Nebraska that are controlling drones in Afghanistan. So this is already happening, right? So with the Internet of Things now, we have massive computation, sensing, inexpensive cameras, and so on. We can, telerobots or multi-robot systems can get their functionality through networking, and sensors, actuators, processors, database, and so on don't have to be physically co-located. You could have what you call a robot that's geographically distributed over a wide area, but everything working together makes that a robot. So here, again, back to our laboratory at UTD, here's 3 robots. It's not a very good video because you can't see the joystick. You'll see at the bottom a joystick. So again, one person can control one robot with a joystick. Like think of your drone controller, right? Here, the robots, all 3 robots are being controlled with a single joystick. Why? Because they have their local autonomy, their local intelligence. They are told basically to maintain a certain separation. And I'll start this. And there you see the joystick, the hint of a joystick there. But the human's controlling all 3. And that scales. It doesn't matter if it's 3 or 300, right? As long as they can maintain their formation, you can control the whole formation with one interface. Okay. So this is, again, an old slide that I put together for another talk. I think it's very relevant today because we had the experience during COVID of having our conferences, meetings, classes via Zoom, okay? And I don't think anybody really liked it, right? Students didn't like it. We don't like it. I attended very few conferences that were via Zoom. I just didn't like it, okay? So here's another idea. Maybe you have a personal avatar. Instead of having a Zoom conference, you're sitting in your office, but your avatar goes to the conference. And everybody has their avatar there. So you could have your company avatars are us. You swipe your credit card, the avatar is at the conference center and goes to the meeting room. Well, this is obviously a disruptive technology impacting transportation, hotels, restaurants, and so on. But it'll increase productivity, right? If maybe there's only 1 or 2 talks you want to hear, so you can hear those in the morning and still teach your class in the afternoon.
Controlling one of these telepresence robots is like using a video chat program with a few extra controls to steer yourself around. You can do most of the things that you would do in person. For example, stopping to talk to people you meet.
The Dominican public is great stuff. Trying to get 2-year-old babies out of the Dominican Republic is difficult.
Or having a conversation as you walk down a corridor alongside someone. Because you can get a feel for the space around you and watch people's body language, those conversations are much like those you would have face to face. I got much more out of our morning meeting as a robot than I would dialing in on the phone as usual, and the people there could talk to the machine as if it was me. Academic research shows that machines that try to act in place of people often encourage high expectations that they cannot always meet. Ultimately, a telepresence robot would always be slightly less slick and less capable than you would be in the same situation. If these robots become more common in the workplace, we'll have to learn a new set of social skills reserved for our colleagues that are machines rather than people.
Okay, so quick summary here. Robotics is all about productivity, right? Automation is all about productivity. But I think that rather than replacing humans, I think the next advance is going to be robots working with humans to augment human productivity, not replace humans. Okay, humans and robots working together will be able to accomplish tasks that neither can accomplish alone. Some jobs will go away. Automation always eliminates some jobs, but creates others, which is not to say it's not going to be disruptive. I think we're entering we're changing so rapidly that we're going to have a huge disruptive phase. And how that shakes out, perhaps, is yet to be decided. But definitely, new jobs will be created if we use it right. We can take advantage of AI and robotics to augment human performance rather than replace humans. So artificial intelligence, as I said, doesn't create the intelligent robots, but improves their performance in well-structured tasks, such as autonomous driving, delivery, agricultural, and forest robots. Assistive robots for the home, elderly care, and so on actually require new social skills. As the video said, we have to learn how to interact with robots. Okay, that's a new social skill we have to do. How do robots understand human intent? You know, grandma's not going to type commands on a keyboard. Grandma's going to say, where the heck did I put my glasses? And the robot's going to have to interpret that and help. Also, humans understand what the robot is doing after it tries to interpret what we're doing. How do we interpret the intent of the robot? So there's a lot of socio-economic problems here, a lot of safety issues, and so on. Okay, so I think I'm probably about out of time. I want to thank you for coming, and I think we may have a little time for questions and discussion. Thank you very much.
Not that Mark needs a moderator, but I was asked to moderate questions. So I see a hand up in the back. Do we have a mic, Aaron?
There was one here.
Yeah, we've got one here.
Okay.
Okay, and then we'll come to him. I didn't see Ari's hand up. But go ahead, Ari, you have the mic, and then we'll go here to this gentleman.
Hi, sorry, I got the mic first. Thank you very much for a wonderful seminar. If we're permitted to be slightly technical, can you tell us an overview from an engineering viewpoint? What are the bottleneck problems that remain right in front of us in robotics?
Well, if we're thinking in terms, so the question is, what are some of the technical challenges, the engineering bottlenecks? And I think one of the ones that people are working on most is perception. Okay, how do we take the raw image from a camera and analyze the scene and decide, you know, is that a mailbox, is that a pedestrian, or is that a stop sign, and so on. So perception is one. And artificial intelligence systems, current state of the art, they're not very robust, as we say. You can take an image and have a small perturbation of the image, corrupt some of the pixels, and it will misclassify rather badly. I think I have a picture someplace here. So the idea of perception, here's an example that I found. So everybody would recognize that as a no parking sign. But people have put stickers there, and the neural network said that's a refrigerator filled with lots of food and drinks. Okay? So again, we have to work in an environment. There's examples in France, for example. People have don't like the highway cameras, right? So they've been going around destroying highway cameras. So if your system is built to take data from highway cameras, you have to worry about capricious people that are going to put stickers on it, deface it, and these sorts of things. But in our not even that much, a very small corruption in an image can cause an AI system to misclassify that image. Okay, as in this example. The other technical challenge, I think, is manipulation. I think we're going to be very good at autonomous driving relatively soon. we're not going to be very good at manipulation, okay? Having a robot in your house to make your bed, wash your dishes, and so on, and manipulate objects, that remains a challenge. And it's because when you're manipulating objects, you have to deal with forces of interaction, friction, sliding, all these are nasty, as President Benson can tell you as a mechanical engineer. How do you model friction, right? It's very difficult, right? And so manipulation remains a big challenge, okay?
Yes, great talk. I have personal experience with the food delivery robot on campus. There needs to be a lot of improvement. I once ran into a situation where the robot got stuck when a facility vehicle was coming off the parking structure pedestrian pathway. So I guess the robot wasn't designed to face that situation. And what was funny was the robot got stuck near the bumper of the facility vehicle, and I could see it. I can see the driver was mortified. I think he thought he ran over the robot and he didn't know what to do. So for about 15 seconds, it was like an impasse between the robot and the worker. So I just went over and picked up the robot and moved it over. So that's kind of a side note for improvement of that robot. Anyway, my real question is...
So you were exhibiting intelligence. The robot couldn't. Your intelligence had to intervene there.
Yeah. Okay. But my real question is, I kind of know the current status of some of those advanced bipedal robot that can run, climb stairs, and I've seen some of the results, but I haven't actually go into the research and the data. But I can see that they are mimicking both an exoskeleton and endoskeleton type combination. So my question is, what do you see the future of this type of application of trying to mimic the, I would say, almost perfect human biological system with a mix of electromechanical and like the exo and endoskeleton? Is it because, I guess part of the reason is there are just too many degree of motion control with, as compared to a true human system?
Yeah. Well, I thought you were going in one direction with bipedal locomotion, and then the other direction is things like exoskeletons and prosthetics and orthotics. I think that's the idea of prosthetic devices and exoskeletons is a tremendous opportunity. I think that that's one thing that is being investigated a lot, and we're making more progress. So again, this human augmentation, human-robot interaction, I think that helping people that have either post-stroke or people who've lost limbs, in the military and so on, I think those are fantastic applications, and I think we're making good strides on that. In terms of the locomotion, walking robots, when you go to Boston Dynamics website, you see very impressive videos. They have made also a lot of progress in walking and running, climbing stairs and so on. But yeah, those robots are still doing what the programmer told them to do. They can balance on their own. We figured out how to balance with feedback control. We figured out how to plan motion of an obstacle and then do foot placement. But it's still basically doing what the feedback control program do. In a way that makes it look autonomous.
Larry, and then we'll come down to Mario.
Thanks for a wonderful talk, Mark. I think you should be the one with the microphone.
I should go back over here. I have a microphone.
Sorry. I have grandsons, so I'm going to put this in the context of that. When I first played catch with my grandson, oh my goodness, it was awful. But after a while, he became excellent. Now he's better than grandpa. And we call that, I think, muscle memory, because he doesn't have to think about it. But can't robots engage in muscle memory? Maybe we call it activator memory or something like this?
Yeah, coordination. There's a concept that's called, I think it was developed originally by Jesse Grizzle at Michigan. He calls it virtual holonomic constraints. And it's basically coordinating your wrist, elbow, and shoulder is like a slider crank. They all move together, right? And then and go look at Raf D'Andrea from the ETH in Zurich. We had him many years ago visit us. He's got these drones that'll fly through, do somersaults and fly through hoops. And the way they do that is basically thousands and thousands of trials, okay? Neural network learning, okay? Reinforcement learning and so on. So if you want to have a robot that will jump over that, well, you let it fall down 1,000 times, and eventually it learns the parameters in the gains in the controller, learns the parameters to do it successfully. It's learning.
But then it's just a matter of looking it up again, right? You just say that in memory and say, okay, now do this?
Yeah, once you've learned it, right? Yeah. Do you realize that when you go to a website and it says, click on the buses, it's got about 6 different images, and click on which one is a bus? You know that you're providing data to train their neural networks? They're using you to give data to train their system.
Mario, and then we'll hear from our 2 students, and then I think we're at the end. We'll do 2 questions also.
So Mark, so you said that automation will increase productivity, and definitely you agree. In your vision of how automation will increase productivity in the future, what happens to energy? Meaning, just the example that you gave, if we train neural networks 1,000 times, we're going to be running electrons 1,000 times through that machine. So are we going in the right trend when we balance productivity with, I would balance it with sustainability, but that's a very vague concept, so I'll keep it at the energy level.
Well, if you're talking about just the energy involved in training the robot, I don't think that's significant. I'm not sure, the energy implications of automation. Yeah, we have tremendous energy implications with electric vehicles, right? We got to mine the rare earth elements and build the lithium-ion batteries, and so on. So and produce the electricity. So a lot of energy implications in transportation in general, even without fossil fuels, right?
Okay, this young man here, next to Julie, and then we'll go to Willie, and that'll be the last question. So Aaron, right here, in the strike zone.
Hello, my name is Gillette, and I'm here with our Nesby chapter here at ETD, and I wanted to know if you had any fear for the future, if, I guess the way that robotics is going now, if we as humans will lose kind of a level of cognition, and like, for example, like we're so familiar with Google Maps now, if you ask them for directions, they have no idea for the most part. Do you fear that there's kind of a more extreme level of that coming to us in the future?
So I was once traveling to UC San Diego to give a talk, and I flew to LAX because I was going to San Diego and Santa Barbara on the same trip. So I flew in the middle, and I was going to go to both universities. So I rented a car, and I'm driving to UC San Diego. Well, I'm driving to my hotel in San Diego, and I got 5 miles from my hotel, and my iPhone battery ran out. I was completely lost. I had no idea where I was or how to get to my hotel. So I found a Starbucks and I went and charged my phone so that I could find my hotel. So I'm very guilty. Without the GPS, I rely on that. I'm pretty lost. So that's a skill maybe that, I don't know, we lose and maybe we don't need it, or I don't know. But related to that is I'm rather pessimistic about the near-term future of things like autonomous trucks, because the largest employment sector in the U.S. are truck drivers. And so if you replace truck drivers with autonomous trucks, then that's going to be hugely disruptive of the workforce. And it's going to increase the wealth gap, right? The people that are building the autonomous trucks are going to get rich, and a lot of people are going to be out of jobs. So, but again, I think that those types of applications, you can have autonomous trucks on the interstate highway from point A to point B, and you can have a driver take over to go that last mile, which is more difficult, to deliver to the house or deliver to the warehouse and so on. So it's not just, we should not just replace a driver, we should work with the drivers and the robots together. But this is going to be very disruptive.
All right, hello, I'm an undergraduate interested in doing research in artificial intelligence, and I was wondering with the increasing automation of tools like with ChatGPT and DALL-E, which can generate images, I'm curious what role will traditional robotics research will play. And I'm curious if you think it's more likely we'll have humans remotely controlling physical robots or humans controlling other humans with robots.
Well, certainly the nature of research is changing. The new generation is, unlike me, is more interested in things like reinforcement learning, okay, using artificial intelligence to produce better robots. So rather than just, my work was physics-based modeling, feedback, control. Now you don't need so much the physics there, you just have the artificial intelligence system that learns how to control it through repeated trials. You got to have 1,000 failures and then eventually gets closer. So that's a trend in research that I see a lot, is more incorporating AI into the planning, control, perception aspects of robotics.
Well, thank you all for coming. Join me in thanking Dr.
Thank you.
Would you like to say to close us out?
No, just thank you all for coming as well, and again, thank you.
Thank you for inviting me. Yeah.